Okay, we'll get started. My name is Alan Rubin. I'm the chair for this second session here at the Science and Data Mini Conference. Our first speaker today is Kevin Plastow. Kevin's a Python developer at the Bureau of Meteorology, working in the Extended Hydrological Prediction Unit. So please welcome Kevin, and his talk is Python for Bridging Between Researchers and Service Operators.
Thank you. Mic's working? Okay. So this talk will be about using Python in the context of hydrology and for streamflow forecasting. So the goal here is to forecast how much water will flow through Australian rivers. I just want to acknowledge my co-authors here, David Kent, Andrew MacDonald, and Deok Shin. So the introduction. So this talk technically is about a software system, C++ software system called SWIFT, and wrapping that software system in Python through a C interface. First, I'll touch on what SWIFT is about, what features it implements, and then I'll go through PySWIFT, what we are bringing in with Python and PySWIFT. And then I'll go through a specific example on a feature that we implement in Swift from PySWIFT. So I'll start with notebooks and go through more of the implementation details, CFFI and Python. This is the Bureau of Meteorology website, mostly used for weather information, but if you go down here, you'll see a water information link. So just click there. You get to this page, water information page. Let's go down here again. And you'll see here in the water forecast section, the 7-day streamflow forecasts. So the 7-day streamflow forecast is a service that provides streamflow forecasts up to 7 days lead time to assist river users in decision making. So just click on here. There are more than 100 forecast locations across Australia for this service. If you go down here, you'll see here, this is the streamflow forecast. And this streamflow forecast is the output of Swift. So just the data is the output of Swift. This is from Swift version 1, which was written in Fortran. But there's a new version of Swift, which is Swift version 2, and it's written in C++. And this will be the focus of my talk. So Swift stands for Short-Term Water Information and Forecasting Tools. This is the basic way it is used. This is rainfall, so just a time series and other inputs as well. Goes into Swift, so C++ Swift. Swift is developed by CSRO and is used by the Bureau through an agreement between the two organizations. So Swift does its thing, and you get streamflow as an output. So this is a bit, it's more complex than that, actually, but I'll skip on the details. Swift features. So Swift has many different models that it uses: rainfall runoff models, channel routing models, error correction models. And all these models have parameters and two main modes. So simulation forecast is what I showed you in the previous slide. And calibration is basically a loop around the simulation. So in calibration, the point is to get some correct parameters, the best parameters for the models in order to deliver a good forecast. So to do calibration, what we do is we pick some parameters, we set those parameters on the models, run the models, and then check the output, and then start again. So the quality of the forecast improves, and then once the parameters stop changing, we stop the calibration. So that calibration is a computationally intensive process. So we need we really need it to be optimized. And to do that, the system is multi-threaded, and it makes use of memory management in an efficient way. So it also has a complex representation of catchments. For this talk, I'll just say a catchment is just a single area, but actually it has a lot of sub-elements. So it's basically a chain of models, like a tree, and at the end you have the streamflow forecast. Now, we are bringing Python here because there are some challenges with Swift. So a typical use case for a user is to load data, change some model parameters, run the simulation, and then plot the results. But to do that using Swift, because it's in C++, the users, the modelers, so hydrologists, would need to do some memory management, deal with some complex data types, and so on. The modelers want to have some quick development, so they don't want to do some compilation, and they also want to do some plotting in an efficient way. So this is where PySWIFT comes in. It abstracts all the low-level data types and memory management, and it has a nice interface that we can use. So this diagram shows you how Swift is used in offline mode. Swift is on the left, PySWIFT. So Swift is used through PySWIFT. Two main modes we can use PySWIFT in an interactive way and through workflows. So workflows just automate some of the use cases that are common to many catchments. But what I'll focus on is more on the interactive use. So for the interactive use, we use Jupyter notebooks, and through them, modelers can set up, tweak, and test simulations. This is a more detailed diagram for the interactive use. On the left here, you see the box is Swift. Swift has a C interface. So the C interface is basically some types and a list of functions. And so what happens is we compile this. We get a shared object file, libswift.so. And this can now be loaded in PySWIFT using CFFI. So CFFI stands for C Foreign Function Interface. It's a Python package. So through this, we can call the C functions. And then PySWIFT adds a nice interface, adds a bit more functionality as well. And then on the right, finally, is the notebooks. So this is what users use. So the specific example I'm going to go through now is Ensemble forecasts. So I showed you the first diagram I showed you was about rainfall in simulation, streamflow out. But now we can have more than one time series of rainfall as an input. And so say in practice, you might have 1,000 Ensemble time series, and then 1,000 Ensemble time series output. So for this example, let's first go through notebooks. Just before I showed you the notebook. So Jupyter Notebook is a way to execute Python code from the web browser. So you can execute Python code and see some plots interactively. And Jupyterhub is the multi-user version of Jupyter Notebook server. So this is what modelers just connect to a virtual machine and see this page. They just enter their credentials and then get dropped into their directories. So I cannot show you, I cannot connect directly to that virtual machine. The Bureau of Meteorology head office is just a few hundred meters away, but I cannot get the Wi-Fi here, so I cannot show you this. So this is what they see more or less when they log in. A list of files. You can browse directories here as well. So I'm going to open my notebook. And this is showing you my example about, of Ensemble forecasts. In that first cell, I import pandas for time series representation and then some PySWIFT components. Second one, I'm loading some synthetic rainfall forecast data. So I'm plotting it here. On the x-axis, you can see in days. On y-axis is the rainfall forecast in millimeters. So this is averaged over the area. And you see 3 lines here. So those are the Ensemble members. In practice, you might have 1,000, but just for the purpose of this presentation, I only showed 3 here to keep things simple. And down here, I can execute that. So that first line here creates a Python object from a JSON file. So basically what this does is when you call this function in Python, it will actually call a C function with that argument. And then what we'll get back is a pointer. So CFFI pointer that is maintained within that model simulation object. I'm creating an object to do the Ensemble forecast simulation here, setting the variable to output, and running the simulation. This is the output. So similarly to the previous diagram, x-axis is the time in days. Y-axis is now the streamflow forecast. And you can still see those 3 Ensemble members. Right. So this is what the data looks like underneath. And what I'm going to focus on is the function, C function, that populates that array here. So I'll go back to the presentation. So I just kept that in case it didn't work. And now let's go to PySWIFT. So in PySWIFT, what we do is create an array. So we actually create a NumPy array in Python. But when we call the C function, we just pass in the memory location of the contents. And then we can just reuse that array. So actually, we're sharing the memory between Python and C. Let's go to the C interface. I'll come back to CFFI later on. So C interface, as I showed you in that example, Python objects maintain a reference to the C pointer. And in the destructor of the Python class, it then calls another function to free that memory. So in our example function here, that first argument, EF simulation, is a pointer to that object that we keep in the Python class. The next 2 arguments are actually not very important here. There's actually 4 dimensions, but we index that to get to 2 dimensions. So basically those 2 are just indexing and reducing the number of dimensions. So finally, let's go to CFFI and PySWIFT. So this is showing you the use of CFFI in ABI inline mode. This is not the preferred way of doing things in CFFI. There's an API mode. But the advantage with this is that you don't need a compilation step. So I'm importing CFFI, and on line 3, I'm declaring a header. And that's what's powerful about CFFI, is that you can just provide your type declarations and function declarations to CFFI, and it will just pass this and provide a foreign function interface for that. On line 8, I'm registering that function. So in this example, I'm just showing this function, but in PySWIFT, there's actually around 150 functions wrapped. Line 9, I'm loading that shared object file. And line 11 is just a regular Python function. So you can see that CFFI actually deals with most of the simple types. So variable identifier is a string. Lead time index, the other ones are integers. So you can just pass those directly to the C function. But for the NumPy array, to share that memory, we need to do a bit more work. And this is what's going on line 15. So this function, what it does is it creates a NumPy array, and then it creates some view of the underlying data that we can pass then to C. So in our example, len y is the number of ensembles, and len x is just the number of time steps. On line 9, I'm creating a NumPy arrays. So the data type float64 in NumPy takes up 8 bytes, and that's the same as in C, C++, usually, on most platforms that implement the IEEE 754. So this NumPy does 0 returns an array. And this array, I'm passing it to as contiguous array. In fact, as contiguous array here is not useful because the NumPy array will be already contiguous in memory when you create it by default. C contiguous, but you can create Fortran contiguous. So as contiguous array, if the array is already contiguous, it will just it will not create a new object. But we have to make sure that it's contiguous in memory before we pass it to C. On line 10, I'm creating a double star star in CFFI. And so this will be our view to the underlying data of the NumPy array. And the good thing about values underscore C is that we don't have to worry about memory management. So once values underscore C goes out of scope, the double star star pointer will just be freed. On line 11 and 12, I'm instantiating that double star star. So I'm just getting the memory address of the underlying data of the NumPy array. This is what the NumPy array looks like in memory. And this is what values underscore C looks like. Now we can just pass in values underscore C to that C function. But when the function returns, we can just reuse np underscore values, and its values will be modified in place by the C function. Okay. Now for the summary. So PySWIFT is a Python wrapper to C++ software system. It has a Pythonic interface and deals with low-level details. In order to use PySWIFT, we use Jupyterhub notebooks. So they have an easy-to-use interface through the browser. And we can get the results from PySWIFT and plot them easily. CFFI is used to wrap the C interface to leverage that C++ code through C. And we can then share the memory between C and Python. Just before I end this presentation, some interesting presentations. I'm not the only one in EHP, Extended Hydrological Prediction, to do a presentation at PyCon this year. So on Saturday, you can see my colleagues Andrew McDonald and Daeok Shin doing presentations as well. So if you're interested in what I talked today, you might be interested in those presentations as well. And that's it.
Okay, thank you for a great talk, and here's your mug. And we have certainly some time for questions, so please raise your hand and I'll come around with the microphone.
Hi, thanks. So have you tried using Python, and if so, have you done any performance testing with Python versus CFFI? Because my experience with CFFI is that it's very slow.
I was expecting this question actually. Python, I haven't tested it in a performance point of view, but I've tested it more on how easy would it be to implement what I'm doing. So there's probably two drawbacks that I find in Python compared to CFFI. So I'm just talking about Python here in the purpose of wrapping some C code, okay? So I don't want to offend any Python fanatics here. And those are, so in Python you have to create a PyX file. You have to do some compilation. So basically you write your binding code in the PyX file, and that makes your architecture more complex. You have to modify the build process as well. And from the point of view of writing the binding code, it's a bit more complex as well, because if you remember my example of a double star star, in Python you actually have to deal with memory management yourself. So you have to allocate, that double star star, check if it's allocated properly, then do a try finally, and then free the memory at the end. So from the, I didn't wrap the whole 150 function in Python, but from my small tests that I did, it seemed like it would be faster to write code in CFFI. But CFFI is used in PyPy quite a lot, so you can expect it to be quite fast.
More questions? Okay, well, let's thank Kevin again.
Thank you.